Welcome everybody to a new episode of Your Friendly Physicist and Other Nerds, your science podcast where researchers speak about their science, their visions, dreams, challenges and their daily life in the fabulous world of science. My name is Lucas and I'm the host of this podcast. Today it's all about batteries and I'm more than happy to welcome Gilles Möhl to the show today. Let me shortly introduce him. Gilles studied physics in Heidelberg and did his master studies afterwards at the Technical University of Munich, where he investigated polymer batteries using neutron and X-ray scattering. Then he moved to Southampton, UK for his PhD, which was about electrochemical processes for bottom-up electronics, like for example batteries. And after that he joined the Soleil synchrotron in Paris to study lithium batteries using X-rays. And currently he's working at the Neutron research reactor FRM II in Munich, and I'm super excited to listen to some insights in his latest battery research and to talk about batteries in general. So Gilles, welcome to the show. Great to have you on board. How are you doing today?
Hello Lucas, I'm very good, and you?
I'm also very well. Now that I finally have you on the show.
Yeah, you finally got me.
So, traditional first question. Gilles, are you a nerd?
Yes, I would say. I mean, I have close to 10 guitars at home, so I would say that qualifies as a nerd.
Definitely. You not only have the guitars at home, but also a bunch of trucks of equipment.
Yeah.
Constantly growing. Okay, let's switch to science. Your science is about batteries. Maybe a very first basic question in the beginning. What is a battery actually?
Yeah, so I think without getting too technical, a battery is something where you can put electrical current in and you can store it for a while and then you can take it out again. That's essentially what it does. So it's, to something to store energy if you want. But I think most specifically, we're always talking about some kind of electrical current that we need to store and that we keep for later.
Why do you think batteries are important for our society?
So I think we want to decentralize where we get our energy from, so away from big power plants to more like scenarios where you would have your photovoltaic panels on your house, for example, on your roof, and you need to store the energy that you get from that, because with the renewables, they only come in when you've got sunshine or you've got wind or whatnot, unless it's water. But that means if you've got these intermittent energy sources, you need to somehow store the stuff, and I think, we're trying to do that with batteries so that you can have different or a lot of smaller points where you collect energy and then you go from there essentially.
So it's not only important to get, let's say, clean energy from solar or wind or water power or whatever, but also to have the possibility to store it in order to have a decentralized grid.
Yeah, it's just to enable the renewable energy sector. Essentially, you need something to store what you make.
So that sounds actually like a very smart plan, and I'm pretty sure a lot of people like you are working on it. But what are the current limitations of the battery technologies right now? So what challenges are we facing, or what challenges are you also working on in your battery research?
So I think the field is mostly working on making batteries with higher energy density, so in both volumetric and in gravimetric, so lighter and smaller batteries.
What does higher energy density mean in simple words? You can put more energy in a same size battery.
Oh yeah. So you have more, exactly. Yeah. So a battery that you would need to charge longer probably, but that you can use longer with one charge. So one charge would give you more electricity if you want. But the idea is, if you had a new battery with the same, that you can use in the same way, but it would be smaller and lighter. That then ultimately you can have more of those batteries with you or in a place because they're smaller and lighter. So in total, you would have more energy stored somewhere. I think that's what people are mostly working on. But the limitations are really mostly material dependent. So I think the lithium battery is already pretty good, and you can see it because if you look at what sizes phones have now, and how long some of them actually last, it's become much smaller, right? And computers as well, laptops and stuff. And that's because just the lithium ion battery has a really high energy density already.
So this high energy density comes out of the lithium ion. So lithium is an ideal material, or one of an ideal material for batteries, because it enables this high energy density. So you can produce very small batteries that you can put on, for example, in your phone or in your computer.
Yeah. Compared to most of the other materials, yes.
What are other materials, for example?
Well, if you think back to your childhood and your Game Boys and stuff, I think most of those were nickel metal hydride batteries, and they were in comparison much bigger than what a little lithium ion cell would be for the same application.
So by changing material to a more suited material like lithium, you basically have a higher energy density in a smaller battery that lasts longer than.
Yeah. It's just the different chemistry gives you a different profile.
Apart from energy density, what are further other challenges that you think are important to investigate right now?
Apart from that, of course, people are looking at safety, and then I guess what goes in with the energy density thing is like the charging and mostly the charging time, because discharging, I guess people are fine with. they know how to do that. Yeah. But decreasing the charge times is also something people try and work on, to not break the battery while doing so. Because typically, you can charge a battery fast or quickly, but tendency is that it will die sooner if you do that. So
rather charge it slow, also discharge it slow, so that the battery undergoes little stress, I would say.
Yeah.
That is good for battery health and lifetime.
Yeah, it could be, but batteries, I always like to to describe them like a string that you're pulling on. Like a guitar string that's always under tension. A battery is the same. So even if you're not using it, it will still be aging, just because it's not in equilibrium. Never. So whatever you do, it will most likely die anyway. But it's true that if you abuse it by doing a lot of cycles, so a lot of charging and discharging, or if you try and get the maximum current out of it. That it will age it faster. So what do you think is from these cutting edge technology lithium batteries, how long is the lifetime right now, you would say? And how many cycles you can get out of it until it eventually ages so much that it's not usable anymore? Good question. I don't know how long you've used your phone. Mine is 3 years old now, and I need to recharge it almost 3 times a day. But that's also because I just use it too much. But I think in comparison, it used to have, it used to work better. A battery is considered broken once it goes under, what was it? Latest under 80. It might be something like 90% of the initial capacity. I don't know. If you want, you can check. Below 90% of the initial capacity. Yeah, it's 90 or 80, something like that, and then it's considered broken. Then it's already considered broken. Yeah. Oh, okay, then I definitely have a broken battery. Yeah, but so if it loses, I don't know, if it loses just a little every cycle, then you quickly get to a point where you don't have anything anymore. That's why that's why people really try and get the maximum efficiency. I mean, close to 100%, because every percent ultimately, then in 100 cycles or something, you're done. Even if it doesn't seem much for one cycle. I mean, for one charge-discharge cycle, yeah.
So maybe to shortly summarize, so challenges are higher energy density, a longer lifetime cycle, faster charging.
Yeah, safety, and then of course, safety. and then getting the materials to build them.
Yeah, that's a perfect bridge to my next question. Apart from lithium, what other technologies, battery technologies, are there right now where a lot of research is going on?
I would say I looked at some stuff yesterday with this, and it's still that everything or anything you find in the periodic table that will intercalate into something or make some kind of alloy is almost being used. So if you look at the first...
Short question in between, what does intercalate mean?
Oh, intercalate. It means that... that's a really good question, actually. So it means that you can put your charge carrier, so your lithium ion, into a material so that it stays in there for the period of time where you want to store it in, and that it also trades or takes an electron in so that you can do the whole charge transfer thing that you need in the battery. But that's maybe not the best word, but anyway, so lithium, sodium, potassium, all of these are being worked on as batteries, and then of the multivalent elements, I mean the ions like zinc, magnesium, calcium, those are also being worked on, and I think some people are even trying aluminium, so that would be a free plus.
So just a recap for the non-chemists among us. So lithium, potassium, sodium are all monovalent, so meaning they carry one electron. Then you have something like zinc, magnesium, they carry two. And then aluminum, is there any other? Trivalent?
I haven't heard of any others, but I guess you could do... I think people are really trying anything they can get to work as a battery, any of the combinations as well.
So having multivalent ions like zinc 2+ or aluminum 3+, they can carry more electrons, so you can carry more, let's call it electricity, from in your battery. But of course they are then probably also bigger, which makes it harder to intercalate or store it in kind of a host matrix where they can stay and get released with a trigger when you want to use your battery. So I think it's pros and cons. So you have a higher charging rate, discharging rate, higher energy density maybe, but then other problems like aging or some lifetime are maybe more severe with these types of batteries.
Exactly, yeah.
Yeah, but then there are basically unlimited types of batteries out there, which all have a faster charging cycle, but maybe less safety or little lifetime. And then others have more lifetime, but slower charging rate, something. So you can really tailor your battery for your particular use. When you don't care about the charging time, because you have time, then you can use maybe multivalent ions, or you change the chemistry within your battery to your needs. So that's pretty powerful materials. Yeah, I mean you said it before. Also, one of the challenges is to get the material. Probably all of us looked in these documentations or these newspaper articles where we get our lithium or cobalt or zinc or whatever from. So is there, I don't know how to put the question, but is this, I mean, for sure this is also a limitation, but do you think at one point we have to, let's say, stop investigating energy and resources into lithium batteries because we basically don't have enough lithium, and then focus on other materials which are much more abundant?
I think I saw something that we are already at the point where lithium is almost done. I don't know how serious it was, But in terms of how much lithium we can still get, even if we made huge progress in lithium batteries, and let's say, I don't know, made them all, that's the thing. The next step from lithium ion is lithium metal for most people, because that's a much better battery in terms of performance and stuff. But that means solid lithium metal parts in your battery, so that means you need a lot more lithium.
So that means when you have only the lithium ions, you still have a liquid, like a liquid electrolyte where the lithium ion is traveling back and forth between the electrodes.
Yeah.
And if you go to lithium metals, the lithium or the charge carrier is moving in the metal.
Oh, no.
Metal part.
No, it's just about so right now the most common anode in the battery is graphite.
Mm-hmm.
But if you replace that with just metallic lithium, then you get an anode with more than 10 times the capacity of graphite, because lithium has one of the highest capacities that you can get. So you would just...
So capacity here means the amount of lithium you can store in an anode.
Yeah, exactly.
Okay.
And if you just make solid lithium, then it's almost the highest. I think silicon is slightly higher, but that's your next big step. But I think, yeah, I digress too much. I think, yes, we probably need, and I think that's what's being done already, to try, if not moving totally away from lithium, to at least have an alternative. And I think that's what is already happening with sodium, because I think there's sodium battery cars already, right? That are, I think some Chinese company is selling those already. And I remember there was when I worked in France, I went to a conference where there was a guy saying that the French also wanted to build some manufacturing plants in France for sodium batteries.
Okay.
And that they were doing it already in China. So, yeah, sodium is probably the next thing that is coming. And then I guess we will just need to go to whatever we can use as batteries, because we need them anyway.
Mm-hmm.
And then if you can't get lithium or sodium, then you just have to use something else to make it work.
What's your guess? What is there? What is the next material?
Yeah, I mean the one I like most is the zinc ion one, just because it's such a friendly looking battery compared to the other ones, because you can just, everything is water in it pretty much, so you can just have it on your desk, and you can put it together and look at it while it's open. Of course, it doesn't so far work very well, so then the question is, okay, yeah, you can have a friendly non-working battery.
Mm-hmm.
But I think if we get it to work, then that would be my favorite so far. I don't know about I think the potassium stuff has very tricky chemistry as well, in terms of, I think they are really corrosive electrolytes that you need.
But speaking of friendly looking batteries and water-based batteries, zinc oxide, or it was zinc oxide,
it's
right?
just zinc 2+.
So also not a very nasty material, so it's actually pretty cool compared to lithium. And you have like electrolytes in there that are corrosive, that can explode, that are flammable. Is this, you think, also a trend, maybe shifting to, let's say, more sustainable batteries, where you use mainly water-based electrolytes?
Yeah, that's being done. I mean, there's also, even for lithium, there's people that try and lithiate materials from seawater, for example, before they. So instead of doing I think usually you would need to do some kind of high temperature process to cook your lithium containing cathode material. And yeah, people are trying to just get it out of brine, and then put that in a battery. I mean, that already I think, if you can use some kind of renewable electricity source to do that, I think then that can be done. And also trying to use more efficient procedures to make the materials. So lower temperature, ambient pressure and stuff. I think that's all things that are tried and tested
during the manufacturing of the battery.
Yeah.
But that also means that right now manufacturing a battery is not at all a sustainable process.
No, I don't think so.
Not yet.
If you, I don't know if you know these, if you've seen these vape pens.
Yeah.
That's a primary lithium cell, but I think this is a thing where you put in a lithium containing battery and then you just throw it away, and that really gets thrown away anywhere, because I don't think people are aware of what kind of technology they are using to smoke.
What is a primary lithium battery?
Oh, that's when it's not supposed to be recharged. So it's not a full battery in that sense, but still, I think.
So it has one discharging cycle.
Yeah,
more or less.
Yeah, exactly.
Okay, and then it's done, you throw it away.
Yes,
it's ridiculous. Even if not the manufacturing process is very sustainable yet, let's say, but how about recycling, bringing back? I mean, of course, it's ridiculous to throw away, even if it's one discharging lithium battery, but throwing it away is ridiculous. But what about like a car battery where there are really massive amounts of lithium in it? How to bring it back into a circular economy? Are these batteries recycled? How hard is it? How challenging is it to recycle it, to get the lithium out, or to replace some components of the battery to have basically a renewed battery and you can use it again?
Well, I don't think it's super straightforward, but technically it's possible, because I think most of if I remember right, the thing that suffers most is probably the anode. So if you and that you're losing lithium inside the battery that you can use, so it will still be there, but it will have reacted to something that doesn't electrochemically participate in the game anymore. So if you manage to, you take your battery, you open it up, and you try and get them and separate the materials again, and that's what people are looking at. So they are trying to divide up the cathode materials. So that would be typically 3 different materials, and the anode as well. So try and get the active material back, and probably try and get the current collectors as well, because there's lots of aluminium and copper that you can probably reuse if you get it clean enough. So, and then refilling with electrolyte is probably the easiest thing. I've seen studies on where they try to do that, and also to try and do it with not too much energy consumption while doing it. So it's a challenge, but it's also being worked on.
So definitely one thing that might appear in the future, might come in the future, to work on both ends, to have like more sustainable materials in the first place, but also to recycle and to bring the not so sustainable and not so friendly materials back into the cycle. Yeah.
Or I mean, another another technique can also be to just not abuse your battery as hard. I don't know if you remember, or if you saw last year, there was a thing with Tesla and the 100-year battery or something. Mm-hmm. And what they did was they used a material that is not new at all. It was just a regular thing, but they said, okay, we're just going to cycle it to a lower potential. So not charge it as much as they could. But if you do that, it lasts a lot longer.
Because your battery, if you think back to the guitar string, is not under so much stress when you have a lower potential, so it's not charged to the maximum, basically.
Yeah, exactly. So this can also be a way, if you say, okay, recycling is really hard, and as you said in the beginning, like if you can play a bit on the application and the demand you put on or towards the battery, then you can also make it live longer, and then you don't need to recycle as much.
Yeah, I see. That's a good point. Yeah. So now that we are slowly approaching the end of this episode, there's one final thing I wanted to discuss with you, and I actually want to go in a bit more detail into your research, and I also wanted to ask you why you are actually working at a neutron source, at a neutron facility. So what advantages does it bring along, or does it add to your research, to your battery research, to use neutrons? And therefore I wanted to start, for the last couple of minutes, a little nerd talk. Nerd talk. So, before we dig right into the details of your research, Gilles, let me shortly explain how a research neutron reactor works. Basically, you have three parts. You have the source, where the neutrons are produced. Then you have the sample, where the neutrons interact with your sample, with your material. And then you have a detector, where the neutrons that have interacted with your samples are collected. And from these information you get from the detector, from your detector image, you can conclude or extract information about your material. So let's start with the source. First of all, we need a fuel element. The fuel element sits in the reactor core. It contains uranium. And to start the reactor, we need only a few neutrons. These neutrons are typically provided by an external source. And these neutrons, you can imagine them as tiny bullets. These bullets hit the nuclei of the uranium atoms that sit in our fuel element. And they make the uranium atom split into two smaller parts. So we have two smaller atoms in the end, and we also have a lot of energy in the form of heat, and we have more neutrons that are released by this reaction. We as researchers, as neutron researchers, we are only interested in the neutrons. So we need a lot of cooling water that takes care of the released heat. And the neutrons that were released, they hit further uranium nuclei, which in turn, of course, provides even more neutrons. So this is our chain reaction, basically. This chain reaction can be controlled by some neutron-absorbing material, for example, Bohr, which sits within or near the reactor core. So this is how neutrons are produced. These neutrons are then guided by so-called neutron guides to the instruments and to your samples. So samples is the second major part here. In Munich at the FRM II we have about 30 different instruments. They are all unique, they can all do different things, so dependent on your material and your research and the things you want to find out, you are looking for a suited instrument. And they can investigate all kind of properties of your samples then. And as we heard from Gilles, a lot of people explore batteries, also in Munich, but there are also other experiments, for example, on solar cells, on superconductors, semiconductors, hydrogen storage materials, new sensor technologies, and a lot more. So at the sample, the neutrons interact with your material. They, for example, scatter and are then collected by a neutron detector, which is our third major component. And from the detected neutrons, how they scattered, how they diffracted, how they changed their energy or their magnetic dipole moment or whatever, there we get a lot of information that we can use to conclude what is happening in our sample. What is the structure, what are the processes, what are the dynamics, and so on. And this is basically how a neutron reactor works. Easy, right? And now we can jump in to your research, Gilles. So tell us a bit more, and in a bit more detail, we're still in the nerd talk, about your research.
Yeah, I would love to jump in. Apparently the water is really warm, right? So yeah, for neutrons and batteries, I think so the good thing about neutrons is that they go through almost anything. without complaining too much. So if you want to look at something that is inherently closed like a battery, because electrodes are facing each other and you need to close them up and seal them so that they work. And so that means you're looking at something that is typically in a metal enclosure or something, so you can't see anything that's going on inside. So trying to understand what's going on without looking inside is possible, but not super easy. So neutrons are a good probe for that, because they go through the battery. And then also what I like about it compared to X-ray radiation, where you can also go through a battery if you want, if you use high energy X-rays, is that you're not disturbing the electrochemistry in the same way with neutrons as you do with X-rays, because X-rays, they interact with electrons, right? And electrochemistry is electrons moving. Mm-hmm. So you get a lot of problems from that, and you can use neutrons in that case to, let's say you want to see how your material lithiates and delithiates during charge and discharge, so you can do neutron diffraction on that, for example, or you could do tomography and see at how your look at how your deposition works. Although I'm not sure how, but that does work in principle. Or you do you do what I do. I'm looking at nanoparticles made from gold, for example, and then I lithiate those, because gold likes to make intermetallic phases with lithium, and then I can look at what the shape and the arrangement of the particles do, or what happens to them in small angle scattering. The issue with all of those things with lithium and the environment, which is mostly carbon based, is that the contrast in X-rays is not really good. So using neutrons, you get much higher contrast, and then you can look at those things.
Contrast means you can distinguish between different materials, like lithium and carbon, like lithium and a graphene anode.
Exactly.
But basically with neutrons, you can then investigate things that happen in your battery, in your closed battery cell, while the battery is working. What you said about your research, so the gold nanoparticles with the intermetallic lithium phases around them, this is then used as an anode.
Yeah, this is so if you're going one step further than lithium metal is no anode at all, because no anode has less weight than no anode. So
but don't you need an anode?
Well, I mean, you don't really, because if you just put a current collector where the anode would be, and you have lithium in your cathode, then you can plate the lithium on your anode part, and then take it back into the cathode and do this all over. So it does work, but the problem is if you lose any lithium anywhere, then you don't have anything in reserve as backup. So anode-free designs only work if the cathode works at 100% efficiency. So anything you put in comes out, and same for the anode. And the problem is actually mostly the anode. If you plate lithium on copper, you will lose a lot of lithium just to side reactions with the electrolyte and whatnot.
And then you have lithium copper alloys or whatever.
No, it doesn't alloy with copper in that case, but you have lithium on copper, but you also have a lot of products of reactions of lithium with the electrolytes. So it would be lithium carbonates, fluorides, stuff like that, and those are electrochemically inert most of the case, in most of the time. So.
And then lithium is lost in these compounds, and you cannot get it back.
Yeah, and then you're just stuck with your battery dying in a very short time, because you're losing all your mobile lithium. So in that case, the idea is to make with the nanoparticles, or with just metallic layers in general, on the anode is to have something that alloys, like gold or silver or zinc also. And the hope is that you can then have a better plating mechanism, and that you can use more of it coming out again.
And with small angle neutron scattering, you investigate then structure of these or morphology of these nanoparticles, how they arrange on, let's say, your current collector, your anode, basically, and how the lithium plates on these nanoparticles.
Yeah, it will plate into the nanoparticle probably. So I've seen already that it doesn't, when I cycle or when I lithiate and delithiate them, I can't get as much current or charge in as I would expect from the amount of gold that I put down. So it might be that if you have a nanoparticle, that it doesn't fully lithiate, so that it might have a pure gold core still, and then outside it would be lithium gold intermetallic stuff. So that's what I can see hope to see. Most of these intermetallic domains apparently are in the small angle or almost medium angle region of length scales.
And these we can see with neutron scattering.
Yeah.
Nice. Cool. Perfect closure of this nerd talk.
Nerd talk.
If you got lost, no worries. You can always message Gilles or me, and we try to answer all of your questions. You can of course also use the Spotify comment section.
There's a Spotify. Right, I didn't know.
There's a Spotify comment section. Yeah.
Nice.
That's really nice. Yeah, maybe in the end, we heard a lot about the future of batteries, what new materials there might be, also start of real recycling, real circular economy. But what do you think is next for you? Where is your scientific journey going?
Yeah, that's a good question. I think I would, if I could just choose, I would do what I do now, just probably forever. So if there were any scientist positions still in Germany, I would take one of those if I got one. But for now, I've decided to do a bit more science still and see if I can get a junior group built somewhere, most probably in Munich. And if it doesn't, yeah, the other day I thought I'm going to do 4 more years in science.
That's a quite specific amount of time.
Yeah, but then I'm 35.
This is the magical threshold.
Yeah, no, if by then I don't think, like, yeah, if by then I'm not seeing anything where I can finish some kind of career in science, because I'm not really, I'm not super well aspiring to a scientific career. But if I could manage to do something in the next 4 years that resembles something close to that, I would do that. And if not, I'll probably do something else.
Something else with batteries, or?
No, I think I would probably leave science and do some cultural work, organize some gigs and stuff. Or maybe the other day I thought I should open just like anyone thinks at some point, I should open a French bakery here.
Of course.
Which means I still have 1 year until I need to start my like apprenticeship for a pâtissier.
In any case, would love to meet you either in your battery research group or in your French pâtisserie. Probably continue talking about batteries or about croissants and guitars. Probably.
They're all the same anyway.
Yeah. Awesome. Gilles, thank you very much for joining me on this show.
Thank you for inviting me.
Take care. See you around FRM II probably.
Or FRM 11.
FRM 11. Okay. Bye.
Bye.
Thank you, Gilles. That's it for today. If you have any questions left to Gilles or me, just let us know in the Spotify comment section or reach out to me either on LinkedIn or Twitter. If you like this episode about batteries, you might also like the episode with Lennart Reb, where we talk about solar cells, why he investigates them in space, and why space applications are also beneficial for our society here on Earth. And as usual, one last information. This podcast is about you, and everyone can participate. So if you want to share an exciting story about your science, your academic life, some crazy experiments, or any other nerdy stuff, feel free to drop me a short message. Thanks for tuning in, take care, and see you soon on the next episode of Your Friendly Physicist and Other Nerds.